Hello, everybody. First of all, I would like to thank the organizer for inviting me to give this talk on my recent works on H-knot tension. The title that I like to talk about is how to think about a tension. In this conference, Hubble tension. But the more formal title is Ginzburg Landau theory of dark energy, and you will see very soon that what are the role of Ginzburg and Landau in my idea. What is Hubble tension? I'm not going through the details of the tensions because you can listen to many talks even in this conference about the Hubble tension and its details. But the tension is that local measurements of Hubble constant, which are model independent, it's important that they are model independent, predicts a value for H naught like 73, but the measurements, I cannot say measurement, the calculation of H naught from Planck satellite, from the CMB physics, from the early universe physics, in the context of lambda CDM model, gives us 67 or so. And then the error bars is very small, and so you see that there is a 4.4 sigma tension between these two values. Here I should say one thing, and then I can go ahead, that during this talk, because I do model building and I do theoretical cosmology, during this talk I don't assume that these tensions are because of the systematics in the observations. It's a possibility, but during this talk I assume that these measurements are correct, and then there is just one possibility for us to make these two measurements consistent, that maybe the lambda CDM model is not the model that can describe the universe perfectly. Okay, so it's my assumption during this talk. I just want to say that there are more tensions and anomalies in the context of lambda CDM, and it's not just the main one is Hubble tension, but there are other tensions and anomalies. One of them is sigma 8 tensions, and you can see in this plot that sigma 8, this gray likelihood is from Planck, early universe cosmology, and these yellow, red, and blue ones are from the local measurements of sigma 8 versus omega matter. And you see, it seems that there is some tension between these measurements, between local measurements and early universe measurement. Sigma 8 shows that how much matter exists in the universe. And there are still more. For example, CMB lensing anomaly. In the context of lambda CDM, you should assume that the lensing amplitude is 1. Okay, but then when you go to TT power spectrum, you see that TT power spectrum is consistent with the lensing if AL is around 1.2 and not 1. And there is, you can see this black curve. And it seems that there is a kind of 2 sigma tension here. This tension, this anomaly, this CMB lensing anomaly is categorized as internal inconsistency, maybe inconsistency in Planck data, because it's not between local measurement or early universe measurement. There is one more here, and actually I had to say there are more, and there are CMB spatial anomalies, and these anomalies, spatial anomalies, are different in comparison to the previous ones, because they are about space. Uh, you could interpret H naught tension as a problem in time, because you could say, okay, maybe there something happened in early universe, but then it changes in late time universe. So it's a problem in the time evolution of our model. But this tension dipole alignment, CMB dipole alignment of quadrupole and octopole in CMB is they are not because of time. It's because of they are in space. So they say something about that the universe is isotropic or not. Okay, and there are more tensions. Void phenomena, maybe core cost problem, maybe, and the other ones. Let's back to our problem. How should we focus on the Hubble tension? Before going to my specific idea and our specific proposal to solve the Hubble tension, to study the Hubble tension, I want to say about my personal viewpoint. My personal viewpoint is that we should not focus on one problem at one moment. We should think about all the tensions, all the problems, or at least some of them simultaneously. Then we can get some ideas that how the universe could work. No? So the reason that I very quickly reviewed the other tensions was because of this. Because I think when we want to think about the Hubble tension, we should have in our mind the sigma 8 tension, CMB anomaly, CMB lensing anomaly, and CMB spatial anomalies, and the other anomalies if they exist. Okay, so now it's time for our proposal, our model, Ginzburg Landau theory of dark energy. We wrote this paper with I wrote the paper with these two very talented guys, Amir Hossein, who was a PhD student at that time, and now he's a postdoc, but he has a degree in medicine too. And my very talented PhD student, Abdul Ali Bani Hashemi, and you will see that many of our works are together. In this paper, we thought that what happens if the dark energy experienced a phase transition in its behavior. Okay, so then you can see that why the name of Ginzburg and Landau came in, because the effective theory for the phase transition was written by Ginzburg and Landau many years ago, and many examples of that, like ferromagnets, Ising models, and many other examples. But the Ginzburg Landau theory is a kind of effective theory for the phase transition, and this means that you can use this their model for any system that underwent a phase transition. It's not for example, it's not just for Ising model. So if dark energy had a phase transition, so we can use the Ginzburg-Landau theory to describe it. Okay. This EF is the free energy for the model, for the system. There is the first term is a gradient term, the second term is phi square, and the third one is phi to the 4. But this small t is a reduced temperature, and it is T minus T critical temperature over T critical. At the mean field approximation, we forget about the spatial structure, so we can forget about the first term, the gradient term. And we have this famous plot, no? Before phase transition, when the temperature is above the critical temperature, we have this dotted potential, and the equilibrium is at the bottom, the point A, and then after the temperature is decreasing, and then it became less than critical temperature, it's some kind of, it's very similar to what happens to Higgs potential. Then we have this Mexican hat potential, and then we have two new minima, and then two new equilibrium, and A goes to B, no? And then it's the new equilibrium for us. So we think that it's true for all the models that did a phase transition. Okay, so for us, the dark energy changed its behavior from the first equilibrium A to B. In our paper, we modeled this transition by tangent hyperbolic, like this, and you can see the details and the results in the paper. But then we thought that maybe we can do a more realistic model based on Landau-Ginzburg theory, because we can solve this equation exactly. And then we wrote this new paper by Abdulali, and then Arman joined us for this paper. And then we said that, okay, this critical, the energy density of dark energy behaves like this. This term came from the Landau-Ginzburg theory. Okay, and you can see that, okay, let me show you the plots. First, focus on the right hand side plot, this one. Here, before the transition redshift, okay, let me say something here. We translate critical temperature to a critical redshift, okay? So this one is related to critical temperature. Before a critical temperature, when for higher Z, for higher redshift, which means for higher temperatures, we didn't have any dark energy, and then dark energy became available after the transition redshift. Okay, so in this scenario, it's exactly like magnetization for magnets, that the magnetization is emergent. For temperature larger than critical temperature, there was no magnetization at the mean field approximation, of course. No, there was no magnetization, but then after the temperature became less than critical temperature, we can have a non-vanishing magnetization. Here in our proposal, a non-vanishing dark energy. Okay. The results are shown in the left picture. First of all, I should say something that sometimes in the literature, of course, if you add H0 data measured by Rees et al., the higher H, if you use that, of course, your parameters change a little bit to take care of that. So your model try to be biased to that parameter. But as far as I understand, it's not a correct way to do data analysis for these models, and then conclude that your model solved the H0 tension or not. The first thing that you should do is you should check your model against just data by CMB from Planck, and it's what we have done here in red. It's just for CMB. Okay. Okay. This name SEDE is critically emergent dark energy. We named our model critically emergent dark energy. So you can see this likelihood, the red likelihood, these gray bands are Rees measurement for H naught, the most recent one. And you can see that our model is consistent with their measurement. So it means in our model, CMB and R19, the Rees measurement of H naught, are consistent, so you can take care of them together. So we did that, and we got this blue likelihood. You can see we predict a transition in the behavior here. I mean the redshift of transition around okay, it's a scale factor around 0.35 or something. And there is no tension between CMB and Rees measurement in our model. Okay. You can go through the details. For details, you can see our paper, but I have to say here that if we add BAO and other data sets there, then the answer is not as good as what we got without them. Okay, let me go back to the main idea. I told you that we are in the mean field approximation, but if we want to go beyond the mean field approximation, we should take care of this term, this gradient term. It means that we should take care of the spatial patches that you could see, for example, in Ising models or in ferromagnetism. No? Here you can see a two-dimensional Ising model. It's a simulation done by Abdul Ali, and then you can see this blue and red points, and then towards the right you can see the temperature is going down, so you can see then you have bigger structures, and at the end you have two very large patches of blue and red, and if you allow to continue for this system, one of these regions will be dominant, and then you have a full red box, for example. Okay, but even so, what does it mean that I said we should go beyond the mean field approximation? It means that we should take care of these patches, and you can see that these patches here they are very small, then they get bigger and bigger, and then you expect the bigger patches when you go to towards temperature 0. Here you can see, okay, it's a toy model, it's two-dimensional, but here you can see something. No? In our model, this blue and this red means two different values for dark energy. Two different values for dark energy. Okay, so you can see that it's unavoidable to have a dipole because one part of the universe is red, the other part is blue. So it means that you should have a direction, a specific direction, a dipole in the universe. For example, through the ISW effect of dark energy. No. If we remove this dipole, you see that there are some features in the region between the blue and the red. No? You can see that red, between them are three blue regions. No? Or maybe sometimes it can happen that there are some remaining spots in the red, for example, a blue spot in the red. No? For whom they are familiar with this CMB spatial anomalies, you can see that this structure is very similar to those anomalies. I have to say that it's just a 2D simulation. We didn't do the calculations. It's in progress, but we didn't do the calculations for three-dimensional boxes. It's very hard and computationally very expensive. But you can see that maybe these structures can be an answer for CMB dipole and the alignment of quadrupole and octupole here. And I should say that don't forget that we start with this Ginzburg Landau theory of dark energy to address H naught tension. Okay, but now we see that the model is rich enough to be a framework to study the CMB spatial anomalies. And okay, one thing more, this recent work that we started with Abdul Ali, that these patches that I told you, what does it mean? They are two different values for lambda, no? So it means that a red dot here in the blue sea, or a blue dot here in the red sea, are some kind of gravitational potential, no? Because they are different with their environment, so they produce a gradient of gravitational potential. So it means that they can be seen by a light ray through the lensing, no? And we did this, and this is a preliminary results. It's exactly for today or yesterday. Here, this I don't know, it's green or yellow, is for lambda CDM with AL equals 1, which is consistent with this lensing potential, but you know it's not consistent with the TT power spectrum. This blue dotted dashed line is the lambda CDM with AL equals 1.2. It's inconsistent with CMB lensing potential, but it's consistent with the TT power spectrum. And our model, okay, it's for some kind of parameters, is this black curve. You can see our model is consistent with the CMB lensing data, these boxes, and it's consistent. It's consistent with AL equals to 1 for high L, but then here for low L's, because of the distribution of those patches that I told you already, it's higher than standard prediction for CMB lensing potential. This higher value maybe in low L, this excess in low L, because there is a convolution when you have unlensed CL to get a lensed CL, you do a convolution. So it can be convolved with all L's, and then it affects all the higher L's, and then maybe this can be responsible for the additional lensing that you see in TT power spectrum. It's a work in progress. Okay, let me conclude here for the first part that we think, at least Abdul Ali and I, we think that this Ginzburg Landau theory of dark energy is a very promising framework to think about the lambda CDM tensions and anomalies simultaneously. I showed you that you could think about H0 tension and CMB spatial anomalies and CMB lensing anomaly together in this framework. Okay. Is there any question? Okay. Based on this motivation that we have in our minds, I started to do some other projects with other colleagues. We said to ourselves that what happens if we do a phase transition in gravitational theory phenomenologically. By phenomenologically, I meant we don't know the exact model, but we model the phase transition by tangent hyperbolic. I did this work with Marzieh Farang, a colleague of mine. And what we did, you are familiar that this omega lambda is is dark energy, and we modeled the phase transition in it with this tangent hyperbolic. And then you know this Poisson equation that k square psi is proportional to the matter density, and there is one way to model modification to Einstein general relativity by putting mu of z and gamma of z here in these two equations, and in standard general relativity, mu is 1, gamma is 1, but you can say if it's modified gravity, you can change these two terms. In this work, we changed these two terms and we modified them by adding a tangent hyperbolic. So they are 1 and then they can be some other numbers, okay? Larger than 1 or less than 1. And so in principle, in this model, we had general relativity, a standard general relativity, and then we had this phase transition at some point. The results shows that you can see the data sets needs prefer a transition of these values, no, except for this mu of z that mu equal 1 is compatible in 1 sigma, but you can see that these the best fits prefer a transition, okay. And we could show that under some conditions, we could address H0, sigma 8, and CMB lensing simultaneously. Okay, it's under some conditions, because then we should add BAO and other data sets too. The other model that I worked on that recently with Hossein Mosafi, a postdoc, and my colleague Shant Bagram, is based on a theoretical idea that I already had, Uber gravity, and then its cosmological version, U lambda CDM, which is done by Shant Bagram and Nima and Natasha. The idea is that the gravity is lambda CDM for densities larger than a critical density, and then it changes its behavior, and the equation of gravity is Ricci scalar equals to constant for densities less than a critical density. And in this work with Hossein and Shant, we showed that in this scenario you can think about H0 tension and CMB lensing together. On the left-hand side, you can see the prediction for lambda CDM. It's H0 versus AL. And you see, if you want to remember that we need AL to 1, because it's our theoretical motivation for, from theory, we know AL should be 1. And from observation of recent measurement of H0, we need H0 to be here at 74 or so. Here you can see from the likelihoods with different combination of data sets that if you want to have higher value for H0, you need higher value for AL. So in the context of lambda CDM, you cannot address both of these equations, both of these requirements. This H0 and this AL equals 1 at the same time. But in the U lambda CDM model, you can see the curves are more relaxed, and then they don't have this behavior, and they become a little bit flat, and then you can get a higher value for H0 while you are you have a consistent value for AL, consistent value with AL equals to 1. So let me conclude. How to think about a tension or a H0 tension. My personal viewpoint is that we should think about many tensions at the same time. Then we can think about H0 tension more. I guess this way of thinking about H0 tension is more attractive for me. I'm more interested in thinking about H0 tension when I'm thinking about the other tensions simultaneously. And we have a proposal, Ginzburg Landau theory of dark energy. As far as we understand, can provide a promising framework to think about all these tensions together, both temporal tensions like sigma 8, H0, CMB lensing maybe, and spatial anomalies in the CMB dipole, quadrupole, octopole alignment, and etc. And let me stop here, and I thank you. And okay, I forgot to put my email here, and I will be so happy to chat with you about the idea and know your critics, your comments, and your suggestion. And for sure, I will be available during the conference. But for